So, welcome back, and this is lecture number 60. We will be talking about Cauchy-Euler equations. So, we will first introduce what are the Cauchy-Euler equations and then their solution techniques. So, here the Cauchy-Euler equations are the equations with constant coefficients. So far we have learned the linear differential equations with constant coefficients. So, this is one kind of special kind of equation with non constant coefficients. So, like here we see this x power n is coming, and then x power n minus 1 is coming with n minus 1 derivative and so on. So, here we will consider this equation which has these non constant coefficients. So, this a 1 a 2 a n they are constant, but together with them we have this x power n minus 1 and x power n minus 2 and so on. So, we will today look into that how to solve such equations when we have non constants in as the coefficients of these derivative terms. So, denoting this derivative here, the nth derivative as this operator d, which usually we do. So, we can write down this equation in this form x power n d n, and then a 1 x power n minus 1 and this operator d n minus 1 operated on this y is equal to x. So, now this Cauchy-Euler equation, now how to solve that, what we will do, we will choose this x, or we will substitute this x to e power z. So, this independent variable z x in the given equation will be replaced by, will be substituted by the independent variable z by this relation x is equal to e power z. That is a trick, and what this trick will do, finally it will convert the given differential equation into the linear equation with constant coefficients. So, that is the idea behind this substitution. So, once we do this one, or we can rewrite this as z is equal to ln x, and that gives us that dz over dx, because that will be required when we substitute all these derivatives terms in the form of z. So, this dz over dx will be 1 over x. So, that is the one derivative which is required now to change the dy dx to the dy dz form. So, now the first change here, because we need to get all these derivative terms change into the z form. So, this dy dx by this chain rule. So, we have dy over dz and dz over dx. So, dy over dz we would like to have now in the equation, and dz over dx is 1 over x. So, we can replace this dz over dx by 1 over x. So, we have this one here 1 over x dy over dz, which we can write down if we multiply this x to the whole equation. So, what we are getting, that x times dy over dx is equal to dy over dz, and that is precisely the point here, because in our equation the order of the derivative here, that is n minus 1th order derivative, then we have x power n minus 1 term. Here when the nth order derivative we have x power n term. So, here with the first order derivative x, and the first order derivative is nothing but the first order derivative of this y with respect to z. So, if we denote here this d as d over dx, this differential operator, then what will happen, that this x into the d here, x into d will be replaced by the second, first let me introduce this d 1 here, which is the operator d over dz. So, having these two operator, the notations here, d 1 will be used for d over dz, and d the standard notation which we are using from earlier lectures as well, that is d over dx. So, in that case this x into the d over dx, because this equation suggests now what we have in terms of this x d operated on y is equal to d 1 operated on y. So, from this equation we realize that this x d operator is equivalent to the d 1 operator, which is written here, that x d is equivalent to this d 1. So, whether we operate x d or we operate d 1, both are the same here. and that will help actually to change this equation into the constant coefficients here, because all these x d and x square d square which we will see now, that will be also converted into d1 form and without presence of this new independent variable z. So, we will convert the whole equation to this constant coefficient equation. So, now coming back to the second order term, how this will look like when converted to the z independent variable. So, d 2 y over d x means d over d x of this 1 over x dy dz term, because this was dy dx. So, d of dx of dy over dx and dy over dx was 1 over x d y over dz. So, we can use this product rule here. So, the 1 over x, the derivative will be minus 1 over x square, and then this dy over dz will remain as it is, plus this 1 over x. Now, we will differentiate this one dy over dz with respect to x. So, that will give the d over dx of dy over dz. So, this operation here will be then minus 1 over x square dy over dz and 1 over x as it is. So, the square will come because of this now here. So, d over dx of this dy over dz will be, so this operation here will be d 2 y over dz 2 and dz over dx, as the case we have done before also when we are taking the derivative here dy over dz, dz over dx. So, here as well. So, the derivative of this dy over dz with respect to z and then dz over dx, and dz over dx is nothing but that is 1 over x. So, here the result of this will be 1 over x into d 2 y over dz square. So, therefore, we got this 1 over x square and d 2 y over dz square. So, what are we getting here? This x square, when we multiply this x square to each term, we are getting x square d 2 y over dx square. The right hand side will be then d 2 y over dz square minus dy over dz. And now, if we write in this operator form, we have x square, the d square term there, and then here the d 1 square and then minus d 1, x square d square is equal to d 1 square from here and d 1 from here, which we can again write down this term as, this term is written as d 1 into d 1 minus 1. So, when we have x square d square, it is converted to d 1 minus 1. When we have x d, this is converted to simply d 1. And now, if we continue this process, what we will get. So, in the general forms, we can now write introducing these operator here, d 1 implies the d over dx and d implies d over dx and d 1 d over dz. So, this x square d square, we have seen that d 1 minus 1. When we compute x cube d cube, what will come d 1 and multiplied by d 1 minus 1 and d 1 minus 2. If we continue this process, in general what we are getting x power n d n is d 1 minus 1, d 1 minus 2, and it will go up to d 1 minus and n minus 1. Yeah. So, here when we have power 3, we are going up to 2, here we have power n, we will be going up to n minus 1. So, this is d 1 minus n minus 1, which is written here minus n plus 1. So, these are the general forms, and we already remember that this x d was d 1. So, we have x d is equal to d 1 x square d 1 minus 1 x 3 d 3 d 1 minus 1 and d 1 minus 2. So, once we know that how this d operator will be changed to this d 1 operator, the d 1 is with respect to z, where d is with respect to x. Then what we will realize that our original equation will be converted to this linear equation with constant coefficient, meaning if we have this f d y is equal to x equation, with that substitution we will get this some function of d1 y is equal to z, and this g d1 will be free from this z, meaning there will be constant coefficients only in this equation, and we know how to solve a equation with constant coefficient. So, let us just go through this example to demonstrate this idea. We have the general solution, we want to get the general solution of this x square d square minus x d plus 2 y is equal to this x ln x equation. So, we will make this substitution, x is equal to e power z, or z is equal to logarithmic of x. Then we know already that if we have this d1 as d over dz, then this our equation here will be converted, because this x square d square term. So, x square d square term will be taken as d1 d1 minus 1, the x d term will be replaced by d1, and plus this 2 operated on y is equal to the x here is e power z, x here is e power z. So, this is given here, and then ln x. So, from here what we have the ln x is equal to z. So, this ln x will be replaced by z, and this x will be replaced by e power z. So, that will be the right hand side here z into e power z, and this operator here with x square d square, we have now the new operator d1 d1 minus 1, and with this x d we have this d1 and plus 2. So, our new equation, which is in terms of the z now, is given here, and now we can simplify this. So, it is a d1 square minus d1 and this minus d1. So, minus 2 times d1 and this plus 2 operated on y, and this gives us z into e power z. So, this equation now is with constant coefficients. So, if we look the coefficients here, is 1, here is minus 2, it is 2. So, all the coefficients here are constant, whereas this in original equation the coefficients were not constant. So, that is the benefit of such transformation, that this equation is reduced now to a equation with constant coefficients, which are easy to which is easy to solve now. So, the complementary function for this equation, because we need to write down the auxiliary equation, that will be m square minus 2 m and plus 2 is equal to 0. So, we have this equation here. So, the roots will be minus plus minus in the root b square minus 4 a c and divided by 2 times a. So, we have 2 plus minus, this is 4 minus 8. So, minus 4 divided by 2. So, we have 1 plus minus, this will be 2 I. So, 2 get cancelled, and we have 1 plus minus I. So, the roots of the auxiliary equation corresponding to this differential equation, we have 1 plus minus I, and that we know how to write down the solution. So, this will be e power, now not x, our independent variable is z. So, this will be e power z, and then C 1 cos z plus C 2 sin z, e power z, C 1 cos z, and plus this C 2 z, that is the complementary function of this equation, or rather to say the general solution of the homogeneous equation, meaning that right hand side is set to 0. So, here this complementary function we have to write down back to the original variables. So, here e power z will be replaced by x C 1 cos, the z was the logarithmic of x. So, cos of ln x plus C 2 sin of ln x, and the p I, the particular integral, will be 1 over this d 1 square minus 2 d 1 plus 2. This particular integral on this z e power z will take us now to this result here, because z e power z, the formula which we have already discussed in the previous lecture, z into e power z into some function of z. So, this e power z we can take, we can bring to the left hand side, and then as a result this d 1 will be replaced by this d 1 plus 1. So, that is what we have done here, e power z we have taken out of this operator, and this d 1 is replaced by d 1 plus 1, d 1 plus 1. So, that was the direct formula which was discussed already in the previous lecture, and now we need to only apply this on this z here. So, let us simplify this one first. So, d 1 is square, and then we will get here 2 d 1, here also we have minus 2 d 1, that will be cancelled out. Here we have 1 and 2 here. So, 3 and minus 2. So, there will be plus 1 there. So, d 1 is square and plus 1 operated on this z there. So, e power z, and then we can bring into the numerator with this minus 1, which now we can expand it, and then we can apply this operator on z. So, here the power of the z is 1. So, we do not have to write down many terms, because d 1, when we expand this one here, what we will get 1 and minus this d 1 is square and plus those higher order terms. Indeed, this d 1, the 2 times when we apply on this z, that will set it to 0, and also the higher order terms will make this z to 0. So, we will get basically only this z, the result of this operation here. So, this is just the z here in e power z. So, that is the answer, that is a particular integral to this equation, to this equation with a constant coefficient. So, what we are getting now, this particular integral, we have to also write down back to in the x form, and this e power z was x, and this z was the ln x. So, our answer is this x ln x, the particular integral, and this is one particular solution of the given equation. And we have the complementary function, we have this particular integral. If we add these two, we will get the general solution of the given differential equation. So, general solution is given by this y is equal to the complementary function, which is given here x c 1 cos ln x plus c 2 sin ln x, and plus this particular integral, which is x ln x. So, this will satisfy our given equation. It has these two constants, two arbitrary constants. So, this serves as a general solution of the given non-homogeneous equation with non-constant coefficients, or the Cauchy-Euler equation. Now, here we will be talking about the idea that there are some equations which can be reduced to this Cauchy-Euler form, and then we know how to solve the Cauchy-Euler form. So, for instance, this type of equation, when we have a plus b x power n, here also a plus b x power n minus 1 and so on. So, these are the coefficients. Now, in the Cauchy equations we have just these x power and n or x power n minus 1 etc., but in this case we have a plus b x, here also we have a plus b x form. So, we need to substitute this a plus b x as a new variable v here. So, if we do that, a plus b x is equal to v, with this substitution our equation will be converted to this Cauchy-Euler equation, and we know how to solve Cauchy-Euler equation. So, with this change, when we make such a substitution, a plus b x is equal to v, with our dy over dx will be written as dy over dv and dv over dx. So, what is dv over dx? That is nothing but b here. So, dy over dx in terms of dy over dv with this factor b there. And if we continue this, if we take d2y over dx2, that will be coming just simply again this one more b. So, that will be b square. When we compute the third derivative, this will be b cube with dy over dv, and this can be continued for any order derivative, meaning that the nth order derivative also we can compute, and this b power n will come out, and then we will have dn y over dvn. So, now if we substitute this into this equation, so what will happen here, this will be having this v power n, and then dn y over dxn will be this b power n and dn y over dvn. The second term will be a1, and here we will have v power n minus 1, and this will be converted again the nth minus 1th order derivative from here. So, the b n minus 1 will come, and d n minus 1 y over dx n minus 1, and this will be continued for this a n minus 1, a plus b x is v here, and dy over dx is this b, dy over dv, and this a n y will be equal to this x, and x is a function of this x here, but that will be converted again, this x will be set to this form of v. So, some function of this v will come instead of the right hand side x. So, when we convert this, what are we getting here? So, by changing that, by dividing this right hand side by this b n, by dividing the whole equation by this b n. So, the right hand side become this x, which again we have to substitute whatever x is given there in terms of v there, and it will be divided by this b n, and then the left hand side here v n and d n y over d v n. Here we will get this a 1 over b here, because there was a term b n minus 1, and when we are dividing by this b n. So, 1 will be survive in the denominator here, the n minus 1th order term, and so on. So, this right hand side again, this is the maybe a new x here, which is a function of v, because this was x was a function of x, but now x is replaced in terms of v. So, we will get also this function of v, the right hand side. But what we realize now, that this equation is exactly the same equation which we have discussed before, this Cauchy-Euler equation. So, the coefficient here with nth order term is v power n, with n minus 1 order term we have this n minus 1, and here we have v. So, this is the Cauchy-Euler equation, which we know that how to solve by this substitution. And now, to demonstrate this, let us go through this example. So, we take this 1 plus x whole square and the second order derivative plus this 1 plus x, the first order derivative, plus y is equal to 4, the cos here with this cos of the log 1 plus x. And now, if we substitute this 1 plus x here as v, I mean whatever given here 1 plus. So, in general a x plus b term here. So, we have taken this 1 plus x is equal to v, this substitution we have made here, and that will convert now dy over dx is equal to dy over dv and dv over dx. So, this dy over dv and dv over dx from this equation is 1, because when we compute this dv over dx, that is just 1. So, that is what here the 1 is coming. So, what relation we have, that dy over dx will be replaced by dy over dv, there is no factor coming because of this 1 plus x. And then the second order derivative when we compute. So, d 2 y over dx 2, again because the factor of this x was 1. So, we will get no change, but we will get just the second order derivative with respect to v. And if we substitute this in the given equation, then we will get v square here and d 2 y over dv square plus the v term and dy over dv plus this y, and the right hand side we have 4 times the cos and ln of v. So, now this equation here is exactly the equation discussed, this Cauchy-Euler form. So, this is Cauchy-Euler form or Cauchy-Euler equation, which we have solved just before by the appropriate substitution of this independent variable to a new independent variable. So, we will do now exactly the same. So, we will substitute here this v, the independent variable, in the form of exponential z, and then by doing this substitution and assuming this d 1 now a new operator in terms of this d over dz, our operator d here is d over dv, the new operator d 1 will be d over dz. So, with that change of this variable, what will happen, this v square d 2 y over dv square or v square the d square, because this we can write down in terms of the d. If we define the operator d as d over dv now, because our differential operator is written in terms of v, then this equation will be like v square d square plus this v d and plus this 1 operated on y. The right hand side is 4 cos ln v. So, this v square d square will be replaced with the d 1 minus 1 and this v d with this substitution v is equal to x e power z. This will be replaced with the d 1 and then this is 1 here, y is equal to the 4 times the cos and the ln v, because v is equal to e power z. So, here the ln v is z. So, this ln v, the logarithmic of v, is replaced by the z here. So, our new equation now becomes d 1 square minus d 1, then we have plus this d 1 and we have plus 1 here operated on y is equal to 4 times this cos z, and d 1 gets cancelled and we have d 1 square plus 1 operated on this y is equal to 4 times cos z. So, that is a new equation now, and d 1 square plus y plus 1 y is equal to 4 times the cos z. So, the complementary function for this, because the auxiliary equation will be m square plus 1 is equal to 0, that is m is equal to plus minus I. So, with this auxiliary equation we can write down the solution in terms of z, that C 1, because e power this is 0 here, e power 0 will be 1. So, we have C 1 cos z plus C 2 sin z, that is the complementary function, and then this z here must be replaced back to the original variable. So, z was ln v. So, we have the ln v for z, and this v was also 1 plus x in the earlier substitution. So, we have to get back to the x. So, this will be the complementary function will be C 1 cos this ln of 1 plus x, C 2 sin ln 1 plus x, and the particular integral which is 1 over this d 1 square plus 1 operated on this 4 times this cos z. So, this 4 we can bring out here, and then this cos z, this is the formula which was also derived there when we substitute this d 1 square minus 1. So, this is becoming 0, and then we have derived that will be the z over 2, and cos will be just the sign there. So, z over 2a, and 2a here is just 1. So, z by 2 and sin z, that will be the result of this operation 1 over d 1 square plus 1 on cos z, that will give z by 2 and sin z. So, this 2 gets cancelled, we have 2 z and sin z, the particular integral of this equation 2 z into sin z, which again we have to get back to v and then x. So, 2 times this ln v and sin ln v, and in terms of x we have v was substituted for this 1 plus x. So, we have to replace this v for 1 plus x. So, finally, the particular integral is 2 times ln 1 plus x and sin ln 1 plus x. And now, the general solution we can write down, we can add the complementary function into this particular integral, and this will be the general solution of the given differential equation, which was first converted to the Cauchy-Euler form, and then the Cauchy-Euler equation was changed to the linear equation with constant coefficient, and that we know how to solve with the help of this complementary function and the particular integral. Coming to the conclusion here. So, we have discussed today the Euler-Cauchy equations, and that is a special form of the equation in terms of the coefficients here x power n minus 1 with the n minus 1 derivative and so on. And we have also discussed the equations reducible to Cauchy-Euler form, and in particular we have taken this form where instead of this x power n we have a plus b x power n, but the idea was simple that if we substitute this a plus b x as a new variable, then this equation can be reduced to this Cauchy-Euler equation, and then again one more substitution will lead to the differential equation, a linear differential equation with constant coefficient. So, these are the references we have used to prepare these lectures, and thank you for your attention.